Ball on a string. Ball on a string. A 0.5 kilogram ball is attached to the end of a string. It is swung in a vertical circle of radius 0.4 meters. At the top of the circle, the velocity is 2.5 meters per second. Draw a free body diagram when the ball is at the top of the circle. Next to that diagram, indicate the direction of its acceleration. Then use the free body diagram to set up the equation needed to determine the tension in the string. And finally, solve the equation for the tension in the string. So we will start with part A, where we're drawing the free body diagram. The string is pulling the ball down, right? You're like this, you're at the top here, there's your velocity. The force is in that direction. That is going to be the tension force. Also pulling you down is gravity, mg, both in a down direction. The acceleration is towards the center, which in this case is down. The relative strengths of the forces is unknown, so don't lose too much sleep over which line here, whether tension or mg is greater. The direction is the important thing. And, of course, the direction of the acceleration. Now, we use Newton's second law to set up our equation. The sum of the forces is ma. And let's see, both forces are in the down direction, so we'll give them negative signs, which you see here. The acceleration is also in the down direction, so we give that a negative sign. We don't like dealing with negatives, so we'll multiply through by -1 to get everybody positive. We then factor out m. It'll make the math a little simpler, removes a step later on. And then we have that acceleration. We do not have linear acceleration. We're going in a circle. So since we have circular motion, we replace the acceleration with v squared over r. That's the acceleration for an object moving in a circle. We have our equation now for tension. And finally, we can put in the numbers. Here's our mass. And notice how it's outside the parentheses, so we only have to multiply it once. We have our velocity, 2.5 meters per second. Make sure you square it, right, the square. Here's our radius. Here's g, gravity. Multiply and subtract it out, and you get 2.9 newtons. Ball on a string, part 2. We have another 0.5 kilogram ball attached to the end of a string. It is swung in a vertical circle of radius 0.4 meters. At the bottom of the circle, okay, bottom this time, the velocity is 4.7 meters per second. Once again, draw a free body diagram, then set up Newton's second law equation, and finally solve for the tension in the string. This time, we have the ball at the bottom of the circle, right? So it's moving like that. That's not a great circle, but it gives you the idea. The string is pulling the ball up, so the tension force is up. Gravity, of course, is always pointing down, and this time the acceleration vector switches. You always have to point to the center of the circle, and when you're at the bottom, the center of the circle is straight up. We apply Newton's second law, which is the sum of the forces, is going to be ma. This time, what signs do we put on everybody? Tension is pointing up, so that's positive. mg, gravity is down, that's negative. And this time our acceleration is up, so it's positive. So there you go. And what do we do then? We isolate the tension force by adding mg to both sides. So we now have tension is ma plus mg. Factor out the m to make the number crunching a little easier. And of course, replace acceleration with v squared over r, since the ball is in circular motion. We now have our equation for tension. We just have to put in the numerical values. And here we have the mass. We only have to multiply it once because we factored it out of the parentheses. We have our velocity. Make sure you square it. Divided by the radius plus g. And we get 32.5 newtons.